Let's take a look at the question, what is a p-value? So the mechanics of a hypothesis test compares our sample data to some initial claim. And this is true for all hypothesis tests. So if we're looking at some test for proportions, for example, we get these really nice normal curves. And we start by assuming the initial claim, the null hypothesis, is true. We create our models. So what this means is in the center of our distributions, we will see our initial claim, our null hypothesis. So if someone tells us that we should win a game 50% of the time, we go, all right, I'm willing to believe you until I see evidence contrary to that. So we start with really sort of an open mindset. It's we believe what we're being told, but we want to compare our data to it. So we then compare our data to the claim. And I'm going to show you two different scenarios that can show up to kind of illustrate what's going on with a p-value and give you kind of a visual definition of a p-value. And then we'll look at the more formal definition of the p-value and see how the two things relate. So scenario one. I've got this nice normal curve. I'm told that I should win a game with a certain percentage. So there's my claim from the null hypothesis. Null hypothesis is always in the center of these curves. And it's possible that our data ends up being somewhere about here. And I'm going to represent our data as some p hat value. So my claim is in the center. And my data is somewhere on that curve based off of that claim. And in this scenario here, the data is pretty close to the claim. So I might think that the claim could be reasonable. Let's look at scenario two. I have my claim in the center always. And that claim is coming from the null hypothesis. So whatever numbers in the null hypothesis you'll see in the center of your models when you're working with proportions. And maybe we're told that we should win a game 50% of the time, like it's flipping a coin. And instead of winning 50% of the time, suppose we're down here at winning like 3% of the time. In this case, our data is so far away from the claim that we might think that is an unfair situation. At a certain point, we stop believing that we're just a little bit unlucky getting lower than that claim value, and we start to think that something is up. Now, in 243 classes and Stats 1 classes, we typically say that threshold is about 5%, that I'm willing to believe something is dumb luck until it starts to happen less than 5% of the time. And that probability that I'm looking at is really the size of this tail here. So in scenario one, I have the data is close to the claim, which makes me think the claim could be reasonable. The null hypothesis could be reasonable. And if that claim is reasonable, this would mean that I would want to fail to reject it. In scenario 2, our data is pretty far away from that center. And if the data is really far from the claim that's in the center, then it might be the case that the claim, null hypothesis claim, is not reasonable based off of our data. Because in general, I trust what I'm experiencing more than what I'm being told. And if this is the case, I would reject their claim of the null hypothesis because I would be experiencing something different. I would have evidence of something contrary to that. Now, mathematically, we need to be able to say if something is close or far from the center. And that's where this p-value comes into play. The p-value is the size of the tail here. So in these pictures, when I'm drawing them out, the center of my curve is the claim from the null hypothesis. The spot where I start to shade on the curve is my data from the sample. And if I have a lot of the curve shaded in, that's telling me I'm pretty close to the center, I have a large p-value. So the p-value is the size of the tail. And I'm going to label all these things. So I'm always going to have the claim in the center of the curve. The data is where I start to shade. So the data is just that vertical line marked on the curve. And the p-value is the size of the shaded tail that creates. And the shading is determined by the alternative hypothesis. So if the alternative hypothesis says less, we shade to the left. If it says more, we shade to the right. If it says not equal, we shade two tails. So the size of the shaded tail is the p-value. So this is a visual approach for what's going on. And I want you to notice scenario 1 and scenario 2. In scenario 1, I have a really, really large shaded tail. So in this situation, I have a large p-value. And if I have a large p-value, this is telling me the data is close to the claim. It's telling me the claim could be reasonable. It's telling me I should fail to reject the null hypothesis. If you have a large tail, that shaded in tail is your p-value. In scenario 2, I have a really small p-value. This itty bitty tail. So large tail here, small tail here. And if you have a small tail, that's going to happen when your data is far from the claim. This is telling you the claim is probably not reasonable for our given data. And it's telling us that we should probably reject that null hypothesis. So when we have a small p-value, when the p-value is low, the null must go. We reject the null hypothesis. So this is a visual definition of the p-value. But let's come up with a formal definition in words as well to kind of match things up. So from this, I would say the p-value is the probability. It's the size of the shaded region. Probabilities on normal curves are just shaded in regions. So the p-value is the probability of our sample data. We start to shade at the sample data. Or more extreme, I'm shading in the direction of the alternative hypothesis. I need a direction to shade. That's what the or more extreme means. So the p-value is the probability. It's a shaded in region, and it starts at the sample data, and it's that or more extreme. So it's this shaded region. But I need to know which curve this is on. More importantly, I need to know what I'm comparing this curve to. So I need to know what's in the center. So this is assuming if the null hypothesis is in the center, if the null hypothesis is true. So the p-value is the probability of our sample data or more extreme if the null hypothesis is true. The p-value is the shaded in region that starts at the sample data and is shaded out compared to this claimed null hypothesis. Now, if you're thinking, well, why can't I just measure far away from the center using this distance here? That's what your z-score does. Your z-score or your test statistic tells you how far away something is horizontally. Your p-value, instead of giving you that horizontal distance, is giving you the size of the tails. So there are really two different ways that you could approach hypothesis test. You could do it using test statistics, using z-scores, or you can do it based off of the region that it creates when you shade it in, the p-value. In most research, the p-value tends to be the preferred method for going through things. So I just want to make sure that you have that same sort of vocabulary as you're looking at this. I think this picture might be easier to understand than the formal definition. So I would start with these things until you feel so comfortable that you start to realize that these two are really the same thing. The picture and the word definition are telling me exactly the same information. So I hope that helps. This was what a p-value is about. And as always, I'm happy to answer any questions that come up along the way.